Hey everybody, in this video lesson, so it's exciting, we're starting our new content for the Grade 10 academic course, and we're going to talk about solving linear systems. So we're going to make use of the review skills we covered in the last two lessons. So here we go. So the first question is, well, our lesson is called solving linear systems. So what is a linear system? Well, a linear system is a pair of lines considered at the same time. That's all it is. So it's a system of lines. Now we will look at primarily 99.9% of the time, we're looking at a pair of lines considered at the same time, two lines. You can have systems of more than two lines. You can have a system of 3 or 4 lines, but we're really concerned with two lines. And if you would like, you can just kind of draw off in the margin here. But if we think about it, what are the different ways that two lines can interact, right? Well, two lines can intersect. Like if two lines aren't parallel, they're going to meet somewhere, right? They're going to meet at some point of intersection. But two lines could be parallel as well. And if they're parallel, they'll never meet. And as we've seen, there are different ways to express lines. So sometimes you might have an equation of a line and a completely different looking equation of a line, but they can wind up producing kind of the same line. So I'm going to just visualize that here. So one line, the lines can be the same line, just in a different form. So our work in this unit will be to look at a pair of lines and how they kind of interact. Do they meet at the point? Are they parallel, et cetera, et cetera. And we're going to be solving linear systems. Just to solve a linear system means to find where the two lines in the linear system meet. And a lot of the time, they're going to meet at a single point. We want to find out where that point is. Sometimes our lines may be parallel and they might not meet, or sometimes we might find out that they're actually the same line. But in general, the 99% of the time, our focus will be, hey, here's two lines that aren't parallel. Where do they meet? And then we're going to see that we can apply this idea to a lot of different interesting applications. So let's continue. So the most obvious way, or maybe not obvious, but using the skills we currently have, maybe a good starting point is, if you have the equation of two lines, we know how to graph. Why don't we graph the two lines and see where they meet? This is a legitimate way to solve a linear system. It's just to graph the lines and see where they meet. So we literally just reviewed this in our last lesson. So can you guys graph these two lines and see where they meet? You're going to solve your first linear system, and we're going to do it by graphing. So I would love it if you pause the video and work through this example, and then unpause when you think you've got it. But if you want to follow along with me, that's okay too. So, and I just want to say too, lots of scaffolding here. So here's a space where you can write down what M is, where you can write down what B is, where you can write out the point of intersection. In practice, all you're going to have is here's equation 1 and here's equation 2, go to work. But I've initially given you some outline here. So for our first line, slope is 2, y-intercept is -8. So -8 and a slope of 2, so up 2 over 1. So this is why I often encourage students to just fill up the whole graph. Because if we fill the whole graph up, our point of intersection should just come out in the wash. It should be pretty obvious. So I'm going to use a different color. I'm going to use green for this next one. Our next line has a slope of -3 and also a y-intercept of -3. So -3 right here. And then we go down 3 over 1. Hey, look at that. There's a common point. Now, just for completeness sake, I'm going to fill my whole graph up. But just to stress, we actually have found the point of intersection. It was that first point we made off the y-intercept. I'm just going to finish, I'm just going to graph these guys. And I'm going to label this guy. That's minus 3x plus 3. I'll switch back to my blue. But as I'm drawing this, we've found the point of intersection by graphing. We've graphed the two lines, and we can see, well, you guys can write down. Excuse me. Where they meet. So y equals 2x minus 8 was our second one. And we can see that they meet at the point x equals 1, y equals minus 5. That is the solution to our linear system. Often I'll just write, so you can write the solution is 1 minus 5. You can write a point of intersection. Sometimes I might just say the point of POI is 1 minus 5. So, oh, it's 1 minus 6, actually. Excuse me. But yeah, there's lots of ways to kind of conclude this problem, but often I'll just use the short form POI. The POI, point of intersection, is 1 minus 6. Hey guys, we solved our first linear system. It's not so bad. You can just graph each line and see where they meet. Pretty cool. Now, in our first review lesson, we reviewed how to check to see if a solution to an equation is correct. Now, how can we check to see, because as we're going to see later, it's not always practical to graph two lines. We're going to learn methods to solve when we can't graph. I'm going to sneeze. Excuse me. It's the beauty of shooting these, is we're going to have little hiccups, and well, I don't have an editing team to edit those out later, so the video continues. So we think our solution, we graphed it, we're pretty sure. We think our solution is 1, negative 6. So are we right? Well, what we're going to do is, if we want to see if we're right, we can do a little left side, right side check in each line. So I'm just going to set up a little t-chart. Left side, right side. And the left side of my first equation is y, and my right side is 2x minus 8. And we think the solution is x is 1 and y is negative 6. So plug in y, negative 6. Plug in x, that's 1. So 2 times 1 negative, I subtract 8. Hey, that's negative 6. The left side and the right side are the same. So I know that 1, negative 6 is for sure on line 1. So that's good. Let's see if it works in line 2. Because if it works in both, it has to be the point of intersection. It's the point that's in common between both lines. Line 2 is y, and then on the right, minus 3x minus 3. And we think the solution is negative 6 for y, and negative 3x is 1. Negative 3 times 1 is negative 3. Negative 3 subtract 3 is also negative 6. Hey, that point is on the second line as well. Well, if it's on both lines, we know it's the point of intersection. We did the problem correctly. So yes, we are right. Now, in practice, if you don't need to do a formal check like this, you could just say, hey, what happens when I plug in 1 to my first equation? I plug in 1, I get negative 6. What happens when you plug in x equals 1 in your second equation? I get negative 6. So these checks you can do in a matter of seconds just on your calculator, and it can give you peace of mind. If it's on a quiz or a test, you just you have those marks in your back pocket and you can move forward with confidence. So doing a check is a great idea all the time. It doesn't have to be formal like this. It can be a quick check on your calculator. All right, let's continue. Can you solve this linear system? So pause the video. I would really encourage you to give it a try on your own, and then unpause when you're ready. If you'd just like to follow along, here we go. So first line, slope is 5, y-intercept is minus 8. So minus 8 and a slope of 5, up 5 over 1, up 5 over 1, up 5 over 1. And for the next one, slope of 3 over 2 and a y-intercept of -1. So I might switch to a different color here. If you're taking this note on paper at home, or even if you're marking up a PDF, switch colored pens or change the color of your marker. If you're, just kind of makes it easy to visualize. Of course, you don't have to do that if you don't want to. You just do whatever you want. It's your note. So -1 up 3 over 2. Would you look at that? That looks like that's our point of intersection. But I like to just, for the sake of completeness, fill up my graph, and I'll sketch both lines. Again, you guys at home can be using a ruler. So there's that line, and I might just color code it. That's that line there. And I'll switch back to blue. Whoops, so this line, pretty steep slope. 5 gives you a pretty steep line. Okay, good enough. And I used dark blue for this one. And so we've sketched both lines. Turns out they meet at 2. 2. Yeah, I had a little panic attack there. I was like, oh, it's not working out to 2. But yeah, 5 times 2 is 10. 10 minus 8 is 2. 3 halves of 2 is 3. 3 minus 1 is 2. So we've solved a second linear system by graphing. Now, we're not going to check this one. Hopefully, you're feeling comfortable at this point. Again, we've reviewed how to graph from slope-intercept form. So it's literally just graphing the lines and just checking out where they meet. Let's continue. So solving a linear system by graphing. Now, I actually kind of regret, I actually don't like using this word because, something that I find easy, somebody else may find challenging. So it's not easy, but it's straightforward, right? That the process is easy to apply. You graph the lines, you read off where they meet. So it's just a straightforward process. You do that, you read off the y-intercept. Now, the caveat is here, the thing is, you can read off the point of intersection if it fits on your graph. Like, as long as the point of intersection has numbers that are, in this case, not bigger than 10 or less than -10, it'll show up on my graph, but that's not always the case. So try solving this linear system. So one more to try. Excuse me. September, it's allergy season for me. If I sound a bit congested. So let's do this one. Of course, pause and unpause when you're ready, or follow along with me. Slope of 4, y-intercept of -2. -2, up 4 over 1, up 4 over 1, up 4 over 1, there. Okay, no problem. And I'll just, while I'm on that color, just draw a line through that. Good enough. Call that my blue line. All right, let me switch to green. How about my next line? Slope of 3 and y-intercept of 5. Okay, no big deal, right? Slope of 3, y-intercept of 5. Let's graph that out. Y-intercept of 5 and the slope of 3. So that's that. Go down here. Okay, so maybe you can see what's happening. So these lines, they're not parallel, right? They have different slopes. And, you can see as they go from the bottom of the graph to the top of the graph, you can see they're kind of getting closer together. So we know that they're going to meet. The problem is they're going to meet way off our graph. So I don't know about you, I don't want to make a bigger graph and just keep plotting these points. That would be very impractical, right? So solving by graphing can break down. It can break down if the solution is off your graph. I'll give you another reason it can break down. So you don't need to copy this down. But let's say you had 2 lines up here. And so maybe line 1 went through those 2 points. And another line went through these points. and the point of intersection would be here. Sometimes the point of intersection isn't at whole numbers. It might be at decimal values or fraction values. And so solving by graphing can give you an idea of where the solution is or what the solution is. But if it's a decimal or fraction, it might be impossible to read off accurately. So what I have illustrated here is that solving by graphing doesn't always work. Sometimes the solution's off the graph. Sometimes the solution is decimals or fractions. So we need an algebraic way of doing this. We need a way of solving a linear system without graphing. So I'm going to tease an algebraic method right now. And then our next lesson's focus will be purely just applying this method. But let's give it I thought we would just give it a try. So we're going to do the two lines that we just worked with, 4x minus 2 and 3x plus 5. So as we saw, the solution is off our page. But let's see how we do this. So I've actually prompted you how to do it. We're going to set the equations equal because it's y equals and y equals, right? So, there's no issue with saying that 4x minus 2 is equal to 3x plus 5. Like if both of those things equal to y, then I can set them equal to each other. And you can see why we reviewed solving equations, because now we have one of these equations we can solve by collecting. At this point, you may not have to show all the steps I'm showing. Hopefully you're practiced up and feeling confident, but you can show all the steps if you want. So we subtract 3x from both sides. We get x minus 2 is 5. So we'll add 2 to each side. X equals 7. So we know that our point of intersection is going to happen when x is equal to 7. Well, what y value does that correspond to? Well, you have two lines that you can use. I'm going to use the first one. So when x is 7, what's the y value for this line? So I'll plug in 7. I get 28, take away 2, get 26. So the point of intersection is 726, which actually seems pretty reasonable. They're going to meet in the positive x values and the positive y values. In 726, that'd even be above my screen here. It definitely seems reasonable. And I would argue that the algebra here is manageable for us, guys. We can do it. So we can solve equations, linear systems using algebra. I've kind of teased a method here, but ultimately for today, what I want you guys to be able to do is solve a linear system by graphing. It also just gives us a bit more time to review those linear relation skills. So I want you guys to try these. The first one, linear system, is in y equals mx plus b form, both lines, so pretty easy to sketch. In our second one, both lines are in other forms, so you might have to use one of our strategies for graphing those from our previous lesson. So pause, try those out, find the point of intersection, and unpause when you're ready. I'm going to go about doing these right now. Now, I will say when I'm practicing and doing a lot of solving by graphing, I might not always just connect the dots with a smooth line. I might just, if I can see what the point of intersection is, I might just call that a day. So in our first one, our line 1, I'll label it that way. I'll label this one line 2 this way. So our line intercept for our first line is 8. And the slope is -1/2, which means we're going down 1 and right 2. So down 1, right 2. I'm going to fill up my graph. And I'll go backwards, and that's all I can get. And then 3/4 times x minus 2 for our second line. Minus 2, up 3/4, up 3/4, got it. And then down 3/4 for completeness sake. Down 3/4. But you get the idea. Oh, I said I wasn't going to draw, but I just did it anyway. Oh, well. That was our line 2, our line 1, Looks like that. And because we graphed each line, we can see what the point of intersection is. The point of intersection, in this case, is the 0.84. So that is our solution. It's the 0.84. All right. What about if there are other forms? Me personally, I just like rearranging. So, because these ones are pretty easy to rearrange. So if you bring the x in this equation to the right, you're just left with y equals negative x plus 2. Call that equation 1. So just that one simple step, put it into y equals mx plus b form. I can graph it now. Y-intercept of 2 and a slope of negative 1. And I just fill the whole graph up because any one of these guys may end up being my point of intersection. So by having a dot there already, it makes it easy to spot. And for our second guy, so if we do the same thing and bring the x over, that gives us negative y equals negative x minus 10. Don't forget, all right, that is negative y here, so we can't just get rid of the negative. But this last step is fine. If we want to get just y equals, well, if this is negative y, we change the sign, and we change the sign on the right-hand side too. So that's the effect of dividing by negative 1. We get y equals x plus 10. So a y-intercept of 10 just at the top of our graph and a slope of 1. So up 1, right 1. Of course, there's no more room on the graph up and right, but we can go back. So down 1, left 1, down 1, left 1, and right there is our point of intersection. And this is the point, negative 4, 6. So our point of intersection is negative 4, 6. And you can actually check this one. It's pretty easy. So this first equation says x and y have to add to 2. Do these numbers add to 2? Yes, they do. The second equation says that the difference, x subtract y, is negative 10. Negative 4 take away 6 is negative 10. So as you can see, checking your answer doesn't have to be a huge process, T-charts and all that. I just did some mental math and I checked my answer and it's good. So I can move forward with confidence. So we can solve by graphing when our lines are in other forms. We just need to put them in y equals mx plus b or find the intercepts, whichever method you like. The reason why I like mx plus b is because it shows you all the points. If you just use the intercepts, you'd be graphing. And if you're like me and not great at drawing by hand, though you don't have those fine motor skills, it may be hard to read off accurately your point of intersection. But by placing the dots, I can see, hey, it's minus 4, 6. All right, guys, we've solved a lot of linear systems by graphing. Hopefully we're feeling pretty good. I just have one example we're going to do an application. This won't take long at all. So we're going to graph a line and for each of these scenarios and use that to answer an application problem. So here the scenario is we have a certain pool. So some pools will just charge you, hey, you want to use our pool, you got to pay $10 a month. And then every time you want to swim, pay us $250. A different pool says, well, no, you don't have to have a flat fee, but you have to pay more per swim. So $350 per swim with no flat fee. So let's graph a line representing each pool's fees for a month. So for pool A, no matter what, you're paying $10. And then you're paying $250 for every additional swim. So if you're doing the math for 2 additional swims, that'd be an extra $5, right? Now I made the grid so that the y values go up by 2.5. So this one's actually pretty easy to plot very accurately. So it's easy to graph pool A. Let's do that. And I'll fill my entire graph up. And I'll just call that pool A. A different strategy would be, I might even do that for the next one. It's just use, instead of dots, you can use like an X or something, right? for your second line. So pool B charges nothing. So it's nothing as a flat fee. So our wind is 0. Then every swim, excuse me, every additional swim is $3.50. So we just have to be kind of just, maybe we'll just keep a mental track of our each point here. So this will be about $3.50, and then $7, just below $7.50, and then $10.50, $14, $17.50. So $17.50 winds up being a perfect point. And then you just keep going up by $3.50. So we're at $17.50, $21, $24.50. We're getting close. $28, $31.50, and $31.50 plus $3.50 is boom. And actually, I said I was going to use different points. So to illustrate that, you could just use tiny x's if you wanted. X, X, boom. We see where they meet. The x's are pool B. I'll maybe just go a couple extra higher. So $38.50 and then $42, just to illustrate that the lines keep going. But we can see we've now got the point of intersection here. In this case, the point of intersection has a very specific meaning. If somebody swims 10 times, it actually wouldn't matter whether they go to pool A or pool B. They're going to pay $35 no matter what. So what we found out by solving that linear system is that 10 swims cost $35 at each pool. Our POI was $10.35. And again, that had some meaning. It meant that 10 swims for both pools cost $35. So you guys did problems like this in grade 9, and then you would say, well, if you were only going to swim less than 10 times, you would choose pool B because it's going to cost less. If you're going to swim more than 10 times, choose pool A. Pool A gets cheaper. But if you're going to swim exactly 10 times, it doesn't matter. I would actually argue that this problem is kind of another good reason why it's good to have algebraic methods. This one wasn't bad because I gave you the grid. But what if you had no grid? Do you want to make this by yourself at home? It's kind of impractical to keep making grids to graph lines to find points of intersections. And even with the grid, with the going up by $3.50 every time, I had to do some work to mentally keep track of where I was at. An algebraic way would be much preferable. And that's where we're headed. But for now, you guys are going to practice a bit solving by graphing, getting used to this idea of what a linear system is. And then moving forward, we're going to shift away from graphing because it can't always be relied on. And we're going to focus on purely algebraic ways of solving linear systems. And there's a couple that we're going to focus on. We'll spend a couple days on each, a couple lessons on each, I'd say. We're cramming a lot of content into single school days this year. But in the meantime, I hope you guys have a great day. Hope you're staying well, and we'll see you soon.